GeomPack. So I'd like to introduce you Jacob Morgan, PhD student here, funded by the project that Reinhard was talking about. So Jacob's talk very much follows in the theme of trying to simulate the process of coarsening in wet fluid.
So yes, the focus of this talk is in two-dimensional simulations of coarsening in wet foams. As has been introduced many times, I think, on the program, the foam is a packing of gas bubbles within a liquid, and I suppose what I sort of in thinking about wet foams, I like to think of Princeton's thought experiment of starting with a container with mainly liquid and dispersed bubbles, and then compressing the bubbles within that container by use of a piston that is permeable to liquid but not to the bubbles, and thereby compressing them together and forming these structures of the type that's in figure 1 or 2, where the structure is determined by the minimization of the surface energy. And so, like towards the end of the previous talk, we consider a complication wherein the surface tension of a film is not necessarily twice the surface tension of an individual gas-liquid interface. The interaction of the surfactant layers on each interface is such that work is done in bringing the two interfaces together to form the film, and consider the case where the film tension is lower as a result of that, and this corresponds to adhesion between the bubbles. That is, the films are energetically favorable to some degree in comparison to two distant liquid-gas interfaces. And so we consider small contact angles of less than 10 degrees. And so as a result, whenever I give equations or approximations and so forth, they're always to first order in theta, just to emphasize that. And so, as in the previous talk, we look at coarsening, and so the small bubbles have high gas pressure. The gas is soluble within the liquid, and so diffuses through it from the small high pressure bubbles to the large low pressure ones. And foams obviously have a lot of applications, sort of carrying things, pushing things, clinging to things, and all of those, I dare say, are reduced by having larger bubbles. The utility of foams is reduced in those cases by having large bubbles, because such things as the shear modulus and so forth are lower. And so we look at we look at simulations of coarsening in the case of a wet foam. And so in the talk, I'll begin by talking about the simulation approach, which will be familiar to those of you who attended the talk last Thursday by Mark Shattuck, because it uses the same approach. I then talk about the implementation of an approximation for coarsening within that model, and then look at the results, including some analytical modeling that helps to interpret the simulation results. And so, yes, our approach comes via Coauthor and co-workers. We consider a quasi-static version of their model, wherein they discretize every liquid-gas interface within the foam, including both sides of every film, as a sequence of vertices connected by straight edges, similarly to Boromend and co-workers, which was related to the work that was talked about last week. We implement this in the surface evolver just to take advantage of its existing routines and so forth. So in order to avoid overlap between the bubbles, the vertices interact with one another via a disjoining pressure. Yes, so we plot the sort of toy model disjoining pressures that we use in figure 5. They're supposed to be reminiscent of the DLBO form, but they're not quantitative for numerical reasons mainly. In order to get a contact angle between the bubbles, we add a little attractive component to the disjoining pressure, the depth of which, so negative disjoining pressure corresponds to an attractive interaction between nearby liquid-gas interfaces, and the depth of that attractive, that minimum in the isotherm, or in the plot there, is determines the contact angle. In order to investigate the case when there is no adhesion between the bubbles due to this contact angle, we also look at a purely repulsive disjoining pressure, which just says the positive, attractive bit of the interaction is sort of cut off. Yes, and so yeah. The H here is the minimum distance between a vertex and an opposing liquid gas interface, and H naught is the value we set as the equilibrium value for sort of well-established long film between a pair of equal pressure bubbles. So our approach to coarsening is an approximate one. We don't solve the Laplace's equation within the liquid. We just take a lubrication style approximation, which comes via Marshall and co-workers in Schilling and Durian, which is to say that the gas flow rate through an element of interface near a vertex, around a vertex, is just inversely proportional to its to the distance between that vertex and the nearest interface. It's as a kind of first approximation that allows you to consider both the gas flow through the thin films and also pick up contributions from gas transfer across the plateau borders, the collection of liquid where the films meet each other, the threefold thing in that picture. By adding up the contributions for each vertex, you then obtain the bubble. For each vertex on a bubble, you then obtain its growth rate, dA by dt. And I think so this kind of thing is well established, and as is and was discussed in the previous talk, the growth rate is, or to understand the growth rate, it seems necessary to understand the bubble pressures and the film lengths of the bubbles, noting that the contributions to this sum are only large when H is small, which that is to say within the films. So obviously we want to consider the flow, we're most interested in the flow through the films because that's the dominant contribution, or is assumed to be. So in terms of the approach of the simulations, we follow Cox, Kreinig, Weir and Hutzler in starting with a very nearly dry foam and then gradually increasing the liquid fraction thereof. Thinking about the Princeton's thought experiment with the piston, it's a case of sort of decompressing the foam, allowing the liquid to be drawn back into it, and so one goes from figure 7, something like figure 7 to something like figure 8. Because we consider relatively small systems, or rather small systems, for numerical reasons, we don't coarsen, or I don't talk here about coarsening the simulated foams through time. We just look at the foams. We look at equilibrium foams as initial conditions for coarsening and look at the bubble growth rates in that state. So, of course, at each of the liquid fractions that we look at, so I'm not sure if I was clear in that the samples. One starts with a dry sample and then gradually in small steps increases the liquid fraction and uses each of those resulting foams as the thing to study, and one extracts statistics therefrom. And one of those statistics that I want to emphasize and was talked about in the previous talk is the osmotic pressure, which in Princeton's thought experiment is the pressure that you need to apply to the piston in order to keep the foam at the specific liquid fraction. Again, as noted before, the osmotic pressure is not necessarily what it would be thought of in chemistry. And so when one has adhesion, as again was talked about before, one has this flocculation effect, which is well known, I think, in emulsions. And this sort of thing is an example of what happens, but there's a great variety of of the structures that you can get out depending on how strong the adhesion is. So, for example, the chains of bubbles that we've seen in the last talk is another alternative as opposed to one big tear as one gets here. So the flocculation occurs because the bubbles have a favored degree of contact with their neighbors resulting from the adhesion. And so if one was to keep them all connected and continue to expand their container, they would all be stretched, and eventually the stretching is sufficient to cause them to detach, and then they form these clusters. So moving now onto sort of the results and modeling. that we get from these simulations. I start with discussion of the modeling of the pressures of individual bubbles. So the simulation results came first, but it's easier to talk about it in this order, I think. So in order to describe this, I start with another definition, the capillary pressure, which I think was mentioned in the previous talk, the area, in 2D, the area weighted mean bubble pressure. And this result, I think, has been known possibly from Princeton or earlier, I think, or in some context, but was proven recently in the general case in 3 dimensions, and it's very easily adapted to 2 dimensions. And it takes the form, so this relationship between the capillary pressure and the osmotic pressure takes the form of a Young-Laplace equation, a sort of equivalent Young-Laplace equation, looking at the aggregate pressures within the foam. And so, sort of, it was interesting, or at least it comes from the results that I show in the next slide, to think of applying the same sort of argument to a single bubble. The argument is then more approximate and with more assumptions within it. And so what one does is one starts with evaluating the average pressure over a bubble, by which I mean specifically in this sense here. So where tau is the stress tensor and tau bar is the stress tensor averaged over the bubble, including the bubble's interface, in order to pick up the contributions from the surface tension in the sense of Batchelor. And then one gets what I call the average pressure, just as minus a half the trace of the mean stress tensor there. And so evaluating after Batchelor what the average stress tensor is, one can relate that to the bubble pressure and to a contribution from the bubble interface. And under the additional assumption that the average pressure is the same for all bubbles, which comes from the simulation results, but I think is sort of along the lines of the sort of widely used assumption of a mean field approximation. And so if one does that and then substitutes the resulting equation into equation 2, you get that the average pressure is the osmotic pressure, which you'd expect. And you get this effective Young-Laplace equation, which I illustrate in the lower panel of figure 9. So that, yes, an effective Young-Laplace equation in which the radius of curvature is the effective radius of the bubble, that is to say, the radius of the circle of the same area, and the external pressure is the osmotic pressure of the foam. So yes, relating it, yes, yeah.
Is that the QV is 2D?
It should. I haven't. Yeah, I think it comes. I think the argument runs the same in 3D. Part of the approximation here is that there should be a 1/1 minus phi here, which isn't very important in 2D, but I think is in 3D. So one would end up with a 1/1 minus phi here, and one would also end up with a factor of 2 there, just from the difference of the mean curvature of a sphere and a circle, in the cylinder. But I think it holds in 3D by the same very rough argument as it was. The same assumptions lead to the same thing in 3D.
Could it be that it's even better in 3D because you've got more neighbors, more averaging?
Quite possibly, yes. Yeah, that seems reasonable. We've looked at simulation, beginning to look at simulations in 3D, but the system sizes have to be so much smaller, it's difficult to come to much conclusion from what we compare. So, so next we have the simulation results, which led to this approximation. And I think what I plot here is the product of pressure and radius, which is to say the ratio of the bubble size to the plateau border radius of curvature. So it's a measure of how compressed the bubble, how deformed the bubbles are, how much their pressure exceeds that which would be expected just by applying the Young-Laplace equation, assuming that they were not compressed. I'm not sure. That was clear. I think. Yes, so maybe, I suppose.
We have some residual scatter around the lines.
Definitely.
Does this break up into well-defined parts? Could you consider, for instance, a number of neighbors?
I haven't found it to now. In the sense that you will obviously get fewer neighbours towards the left and more to the right, but I don't think they don't seem to form
Okay, so
clusters.
the scatter is not due to this.
I don't think so, no. And so, I suppose a consequence of this, a consequence of this approximate expression for the pressure is that the smaller bubbles are less deformed than the larger ones. That is, as one moves towards the left, one considers smaller bubbles, and then the excessive pressure over what would be predicted if I ignored the osmotic pressure is smaller, so that the smallest bubbles are undeformed, which I think is intuitive in the sense that if one imagines building up the foam by just popping bubbles in time and time again and decreasing the liquid traction that way, it's easier to fit in a small bubble than it is a big one without disturbing its neighbours and thereby compressing it at all or deforming it, is what I mean. So we find that the same. So yes, I should say that the straight lines there don't involve any fitting, but the osmotic pressure is taken from the simulation, so that it's not independent. In figure 11, we see that the same thing with more scatter is observed. The same rule appears to apply for a non-zero contact angle, remembering that the contact angle is small. If one considers a larger contact angle, there will be terms in here from the film length, and that complicates things, and we haven't looked at that in great detail.
Could it be that the scatter is somehow related to the state of relaxation of the foam? If you just throw together a few bubbles, they will be distorted shapes, and any training likes to cycle around this bubble stretch, it's going to drive it into a deep energy minimum. If you did this kind of relaxation, possibly you have less distorted shape and a closer correlation. Could that be?
We do the annealing process of training, yes, but we only do one cycle. So we haven't tried varying the number of cycles, for example. So that would definitely be something we could do. We anneal, so doing a sequence of extensional shears, and we also relax the stresses of the sample as well, the microscopic stresses.
And since you have this special expression to evaluate local stresses and structure, is there some relation between local stress fluctuations on the one hand and the scatter on the other hand?
Very interesting. We haven't looked at it. Yeah. I think so. The last point I want to make here is that it's been common, and I think it was mentioned in the last talk, when developing models of bubble growth rate to, as a first approximation, take the differences in pressure of a bubble and its neighbours as those given by the Young-Laplace law. And I think that this kind of model and the simulation evidence in support of it does support that use, in the sense that if you take the differences in bubble pressure, you just lose the osmotic pressure cancels out, and so you have a difference of terms of this sort, which is what you'd get if you were looking at pressure differences within a foam where the bubbles weren't distorted at all. So given that we have an approximation for the pressure that seems to work reasonably well, it was interesting to think of whether this could be applied further in modeling the other important aspect, or another important bubble property for looking at coarsening, that is the film length, or in particular the proportion of the bubble's interface that is covered by films as opposed to in contact plateau borders of liquid. And so again, taking sort of some ideas from the work of Höhler and Segnaghi and Kreinik, sort of thinking about the relationship between the averaged pressure of the bubble and the forces exerted on its boundary by its neighbours, is possible to show by which I assume that this result is relatively established, the relationship between the average pressure and the and these forces exerted on the interface. But one can go further, of course, and with approximation, and knowing that the forces exerted on a bubble's interface are due only to the destroying pressure, thinking of foams at equilibrium as we do, so that there's no liquid flow, and so no viscous forces and no body forces either, resulting from gravity or anything like that. So little f is related to the disjoining pressure alone, and that can be estimated within the films and can also be estimated to give a singular contributions at the end of the films due to that little attractive component to the disjoining pressure as the interface of the film move apart from each other, which gives rise to the contact angle. And so by putting those into equation 4 and making further approximations, in particular that the bubbles are circular, which of course they aren't, but one gets an approximation for the film lengths after rearranging. So again, we can compare this with the simulation results, and of course it's clear at low liquid fractions here on the left that the film length isn't a single valued function of the radius, but still in developing models of bubble growth rates, it's possibly a useful approximation to find a sort of a rough approximation for the film length as a function of the radius. And we see that the approximation, I think, does reasonably well in capturing the variation. Again, the osmotic pressure is taken from the simulations. The equation I showed before is not a function totally of the bubble radius in terms of the bubble properties. We also have the number of neighbors there, which we don't have an approximation for the number of neighbors as a very approximate single valued function of the bubble radius as yet, or at least not a good argument for one. But nevertheless, if one looks at foams that are either very wet or have the foams that are very wet that have flocculated due to the bubble adhesion, they've clustered, then you can divide obviously through by the number of neighbors and look at the length per film as a proportion of the total perimeter of the bubble. And again, we see a reasonable approximation. I think there's clearly a little bias, but I think for the simplicity of the approximation, I think rather pleased, I think. So another sort of thing that one can work out from that bubble-wise expression for the bubble radii, bubble film length, is we can estimate a mean, and I don't have a sort of a strong or rigorous argument as to the means of estimation, but just sort of as an estimate thereof, one can replace the radius by an average that turns up very frequently in these problems, R21, which and replace n by its average in the whole foam, and then we get equation 6, which is of the same form in 2D as compared to in 3D of the existing results of Fuller, Signagi, and Kranik. And we find that in comparing this result to the simulations, that the agreement is fairly good, I think. The error bars there are just to give an indication of the spread in, so it's the standard deviation of the film length distribution, just to give an idea of the variation, the magnitude of variation in film lengths between bubbles.
Okay. Can you remind me? So L is the perimeter of the bubble.
L is the film length. It's the length of all of the films added up around the bubble.
Yeah. But is that the same as the perimeter?
Because it's a wet foam, the bubble will also be in contact with a lot of liquid in the form of plateau borders. So L is the sum of the lengths of these thin films. And then
in contact with another.
Yes, yeah, sorry, that's the yes, no, that's better way of saying it. Yes, yes. In terms of prior work looking at the mean film lengths as a function of liquid fraction, we're in qualitative agreement with some work that was done at for zero film thickness. I realized that there was something I had meant to say when describing the model, the simulation model, which was that for numerical reasons we're at the moment restricted to having quite relatively thick films, orders of magnitude thicker than one would get in a real foam. We tend to use the film thickness of about a hundredth of the mean bubble radius. this will obviously affect the result somewhat, but it would be interesting to investigate the extent to which that occurs. We have not done so systematically as yet.
Could you just artificially change the film thickness in your calculation?
The difficulty, certainly with bubble growth rates, is that the discretization will obviously be, on some level uneven, and so I haven't thought how it will be possible to make sure that within the films, for example, supposing I want a film thickness of, a very small film thickness artificially, then if I were to just subtract off a value from the actual film thickness I measured within from the simulations, then because of just the non-smoothness of the discretization, I'd worry about the fluctuations within the result that I would get, if that makes sense. That it may become negative, for instance, if I were just, so I haven't thought of a sophisticated way of doing it.
I was thinking of something really simple-minded, where below some threshold, which is slightly above what you consider at present film thickness, for parts which are thinner than that, you just do as if it was a lot thinner than that. So there would be a mismatch somewhere, but this is only in a very small region. So potentially this would not be a big error, or might even deal with this mismatch analytically.
I think I suppose I do worry a little bit about the mismatch, in the sense that so one can look at the growth rates, for instance, of the bubbles, looking just at the gas flow through the films. But if one wants to look beyond that and obviously look at the additional contribution to the plateau borders, then the mismatch might have quite a large effect there, or perhaps, as you say, the analytical modeling would be more appropriate.
Okay, but if it's just a triangular cross-section, it's a kind of meniscus with triangular cross-section at this very small scale, possibly this could be that.
Yeah.
Sorry. So for the repulsive simulation, so the fact that this goes to 0 at 0.15, is it the risk of uncertainty?
It should be the jamming transition, I think. Yes. It should be the point at which the bubbles lose contact from one another. So because of the clustering that one has when there's adhesion, one never gets to that point, at least not in these simulations. And so you have a plateau resulting from the fact that the clusters don't change very much when you continue to add liquid within. So for example, in the lower picture in figure 8, if I were to add liquid continually to that, then all that would happen is that the gap would become bigger. Whereas in the normal case, with no adhesion, one would get the ordinary jamming transition, and all the bubbles would move apart from one another.
And is that 15 or 0.15? And they said what you want to have the expectation.
I think so, about 16% for monodispersed disordered case. Yeah, monodispersed disordered case in 2D, I think it's right. About 16%.
This will do that with this.
So having looked at the bubble pressures and the bubble film lengths, our interest is in coarsening and the growth rates of these bubbles, and so that's what I'm here from the simulations. And so at the low liquid fraction, we get this level structure of the growth rates with the levels corresponding to distinct numbers of neighbors, which you'd expect from von Neumann's law, which would give the growth rates as the integers with this scaling. And then the deviations from that have been looked at by other groups such as Roth and co-workers and Schilling and Durin that I mentioned earlier. And we find that we're in certainly in qualitative agreement, but also I think in quantitative agreement when you take into account the gas flow through the plateau borders, which will be relatively large in proportion as a result of our thick films. As a result of the fact that we don't look at the time dependence of these systems, we just look at them as initial conditions, it would nevertheless be nice, I think, to be able to say something about how quickly coarsening would progress it were we to allow it to. And so as a proxy for that, given that the mean growth rate of a bubble is 0 by the conservation of the gas in the foam, I think it's reasonable to take the width of this distribution of growth rates as a proxy for the initial coarsening rate within the system. And so that's what I've got here as a function of liquid fraction for different levels of adhesion between the bubbles. So I think in particular, I think it's interesting that for the repulsive case as compared to the 0 contact angle case, which perhaps confusingly does include adhesion as a result of our finite film thickness, in the sense that if one is to bring a pair of liquid gas interfaces together in order to form a film, in order for the contact angle to be 0, the film tension must equal twice the isolated interface tension, and so the total work done in bringing those two together must be 0. But we know that the distraining pressure must be positive, must be repulsive at equilibrium, and so there must be a little attractive component in order to balance it out. And so that's why you get adhesion at 0 contact angle with a finite film thickness. But nevertheless, the curves remain very close up to the jamming transition, where they do separate quite substantially. And I think, yes, as a result of the formation of these chains of bubbles that were mentioned in the previous talk, there's a little sort of kink there in that, well, not a kink, but a change in behavior at the jamming transition, which will be the result of gas transfer going from being through the films between the bubbles to going through the plateau borders exclusively, or going through the thicker conglomerate, thicker collections of liquid exclusively.
Would this be something which is the same from sample to sample? You showed this fracture, which could be implemented in various ways. So you get a dispersion if you do simple, different random realizations of your simulation.
What I find is that depending on the cleanness of that fracturing, the plateau value will differ slightly of the upper curve here. But we have repeated it for several samples for smaller systems, and we find that these sorts of curves are consistent between them. I think that particularly if one was to plot the mean number of neighbors of a bubble versus liquid fraction, there is a sensitivity to the final value resulting on how the flocculation occurs, even at a fixed contact angle.
Do you get brittle fracture irrespective of contact angle?
We haven't looked at sort of the. I wouldn't be able to definitely classify what's occurring, but in terms of qualitatively, it appears that small contact angles give rise to a ductile fracture where you have chains of bubbles, whereas you get these big tears, what might be a brittle fracture at higher contact angles, which thankfully or interestingly, coincidentally occurs at about 10 degree, is present at 10-degree contact angle, which we consider.
3-degree curve would look like something intermediate, or if one. So there are two definitions of the contact angle. The definition that comes from the film tensions, and the definition that comes from actually measuring the contact angle. And we find that when we measure the contact angle up here on the curve for 0, sort of 0 set contact angle, the measured contact angle is about 3 degrees. But if one were to set 3 degrees, then yes, the curve would be a little higher. Yes, yeah. That disagreement just comes from the finite film thickness, and possibly the definition of measuring how we measure the contact angle as well. We fit circles to the film interface and to the plateau border interface and see what angle at which they meet, which comes from a paper by Denkoff, and I think is almost the standard one, although I know that there are other ways of doing it. Depends on where you choose to consider there is a transition region. But we can talk in detailed aspects later.
So I should maybe mention that this sort of plot isn't representative of foams of higher liquid fraction. The geometric constraints that give rise to von Neumann law break down as plateau borders are no longer meetings of 3 films, but can be meetings of 4 films and higher, and one then fills in the gaps between these levels as a result of bubbles losing neighbors. And in fact, one can see one instance of that already, even at 2%, which I checked earlier today to make sure it was what I expected. That is that it's a six-sided bubble that is very nearly in contact with a very small bubble that is therefore supplying it with a lot of gas, and therefore it lies within the n=7 level. I think so. The final sort of pre-conclusion slide, being sort of combining the analytical approximations together in order to get approximate growth laws. So this sort of approach of, so what one does is takes the bubble growth rate to be proportional to the pressure difference of the bubble from its neighbors. The neighbor pressure is set by conservation of gas under coarsening, so the mean growth rate should be 0. So multiplying that pressure difference by the film length in 2D that the bubble would have. That's a standard approach coming from Lemlich, and applying that with the model for the bubble pressures, and assuming that all bubbles have the same fraction of their surface covered by film, that is to say in contact with other bubbles, you get a result that is the 2D version of something that has been looked at in 3D or has been proposed in 3D by Pasquet and co-workers. But one can also take into account the variation of the proportion of bubble interface covered by in contact with other bubbles, how that will depend on the radius of the bubble. So that's what one gets. That's equation 8. So multiplying the pressure approximation with the film length approximation that was argued for earlier, and so we can compare that with the simulation, just looking at the root mean square growth rates. The agreement is not great, but it nevertheless indicates that it is not wholly incorrect. Of course, it's difficult to say what is coming from where in terms of the agreement, because the osmotic pressure, the mean number of neighbors, the number of neighbors, the radius are all taken from the simulation. So it's just, I think that plot is more just an indication that these models are maybe not completely, yes, that even though there's a lot of approximations in there, they're able to reproduce somewhat qualitatively the behavior. And something else that can be done with these, noting that equations 7 and 8 don't really disagree very much in terms of the root mean square growth rates, is to look at is to use these following Lemlich to look at to look at the scaling state properties of the foam by considering a large number of bubbles, each of which only sees the mean field around it and grows in accordance with these laws. So obviously much simpler than the simulations I've shown, but nevertheless able to look at very large systems. And then one can look at the bubble size distribution that coarsening should give rise to, and then it might be interesting to compare these models there. In particular, with regards to what was talked about in the previous talk, the excess of very small bubbles that one sees at lower liquid fractions could, possibly be related to the fact that, I assume it's quite sure that it would be related to the fact that very small bubbles are not strongly deformed by their neighbors. But nevertheless, it would be interesting to see if something like this would be able to reproduce that qualitatively. I should say that RC here is the critical radius, which is again, what I mentioned before, just being set by the conservation of the total gas in the foam. So in conclusion, I've presented some results of some simulations of equilibrium foams in which we're interested in properties that relate to the coarsening of those foams. Talked about some analytical approximations that I think help to interpret those results. our current work is looking at 3 dimensions, where the system size obviously has to be a lot smaller. But the same techniques can be applied, and we hope to generalize the analytical approximations to that, in particular the film areas. And just to relate that back to the previous talk, that it's sort of the intention is that some of these results should hopefully help to interpret the recent experiments done on the space station. So I thank you very much for your attention, and I welcome any questions.
Nice talk, really, so many good results. It looks as if you have all the ingredients to build a model that predicts how the distribution of sizes would evolve, starting from any initial distribution towards possibly a scaling state. Do you see any obstacle to doing this, or is it just that we haven't done it yet?
Just that we haven't done it yet. Yes, yeah.
You need to build more suppression.
Yes, I think. I suppose, yeah, there isn't a theoretical, in two dimensions or 3 dimensions, I think there isn't a theoretical expression of osmotic pressure or approximation for osmotic pressure as a function of liquid fraction, and especially not for a non-zero contact angle. So it would be the scaling state properties as a function of osmotic pressure as opposed to as a function of liquid fraction. Yeah, that's quite right. Yeah.
Second question, how this approach that we use, each interface is individually represented compared to standards, so that you will in terms of computational efficiency. Of course, but you are much more efficient because you don't have any issues with D1s, I imagine. But comes just convergence. Is this 10 times slower or similar, or?
Afraid I don't think we've made quantitative comparisons between those 2 types of simulations. I think in terms of execution time, they may be comparable, just on the memory of how long certain coarsening simulations that we did took, but I couldn't be quantitative about it. Yeah.
It is slower because you have more points, and the standard surface over evolution is compiled into the program, whereas evolution that we're talking about is not. So it's less efficient in that sense. But you have to make all the same decisions about how many points you want, how many makes, how accurately you want to represent the curve. It goes to 4, 5.
Yeah, so about 96 vertices per bubble. About 96, about 100.
Again, comparing with what Mark showed last week, is very well refined. And we won't go away and do 2 hours to put that.
No, they take about maybe. I think the runs that I showed the results of today probably took of the order of 900 hours. I think with 256 bubbles, it's about 90. So I'm not sure if everything is efficient as it should be in terms of the scaling and so forth with the system size. But I think it's different. Yeah.
Could you give some details on the potential you used for the interaction, and also how you define how this purple X? Because I would imagine that they are not really in contact. There is some threshold.
So the interaction potential is implemented just as the integral of this curve plus the contribution from the surface tension. Maybe I should write. So I think so the surface tension of one interface of a film of thickness H, I think it's a standard result that is yes, the surface tension of, so to speak, an isolated liquid gas interface, which I might call gamma infinity, just in the sense of it's the subextension of an infinitely thick film, plus a half, just because obviously there are two sides to the film. The integral from h to infinity of the disjoining pressure. And that's the sort of the equation that in effect we use within the simulations. So given a toy model for the disjoining pressure, then that can be obtained. As in terms of the numerical details, it's just, I think, the way that we did it, which might not be the best way. This term is taken in the usual way in the surface evolver as being summed over edges. This term is sort of added on as the sum of vertices. H is determined, so it's I've said the minimum distance, or it's the minimum distance from a vertex to an opposing interface. And the way one does that is to find the closest vertex on an opposing interface, which is a long step, I think. And then one, so if one is looking at vertex, one is wanting to find H for vertex A, one finds its nearest neighbor as vertex B, I should say nearest neighbor on another interface. And then, so from vertex B, you have its two neighbors and the edges that join them sort of directly from the surface evolver, from the way it keeps track of things. And then the distance that we use is, I've probably drawn that wrong, is the shortest distance to this sort of apex of the triangle. With these two ends extended to infinity, but that shouldn't make much of a difference, as it were, with the smooth shapes of the bubbles you get in an equilibrated foam. Sorry, can you remind me what the other bubbles?
And the foam length.
Ah, yes. In order to hopefully try and avoid any thresholds or anything like that, trying to think, yes, that a natural definition is to fit a circle to the film interface. What do I mean? So if I have plateau, okay. I have a plateau border, and then say a film, and then another plateau border. Then I can identify the films by the vertices that are experiencing a positive disjoining pressure. So I know that a vertex here is in the film for that reason. And then given sort of identifying the vertices which are in the films, I can then fit a circle to this interface here. I can move away from these, from this film vertex that I've identified until I find myself in a plateau border on either side, and then I can fit circles to the two plateau borders, knowing their curvature from, say, the Young-Laplace equation, and then I can work out the point of the intersections of these. They give me the contact angle, that was the measured contact angle I was talking about before, but they also give me the film length. So that's the way it's done here, and it is a very good question, because that is a difficult thing for simulations.
Thank you. To what extent is this a problem of understanding the random assembly of all bubbles, as opposed to understanding how the physics depend on the shape of an individual bubble? And I suppose to put that a little bit more into context, Andy Kroenig and a few others, they for 3D coarsening of dry films, they came up with these very nice single cell models where you could kind of study, you know, actually the ones that are exactly displayed on that picture there of the Aberystwyth banner, right? But it was basically kind of coming up with a model where you can create individual film cells that are then, so in this case, suspended from frames. And basically you could answer the question, to what extent does the topology and also the shape of an individual bubble determine the bubble growth rate? Right? Yeah. So I suppose in that context, to what extent could you come up with a single bubble model to probe the things that you have studied in this multi-cell simulation?
I suppose the focus that we have had is on the individual bubbles within the foam and looking at their properties and seeing how they're related to their growth rate. But I think it's true that we have mixed everything together a little bit in terms of averaging out the neighbors and so forth. So I suppose I wouldn't expect, for example, the approximations here to work for individual bubbles necessarily quantitatively. If one was to look at say bubbles made on a frame or something like that, I wouldn't expect these things to apply to that necessarily, but instead I think there are lots of assumptions that are sort of hide within how maybe I see these things of sort of going from sort of a rough model for an individual bubble and then going on to looking at how that affects the properties of the whole foam.
That's connected to your talk to Reinhardt's talk, right? Of course, Reinhardt just told us that there's this beautiful scaling state, right? Which will be the natural state, right? And that's really what you want to know, what the growth rates are for, right? Because you're not starting from that, you don't have that scaling state, so your spatial statistics, if you want, are not representative of the state that we know a real has. And so in that sense, I suppose I'm curious to what extent would it make sense to kind of think about an effective single cell model where you can then afterwards kind of model the statistical effect that comes from the ensemble basically as a sum.
Yeah, I'm not sure. I think I need to think about that. I can comment maybe on one point, which was the initial size distribution. We tried to have something that is representative of a coarsening foam just by sampling from a distribution that was found experimentally by Ross and co-workers, which we'll be able to find, I think. Yes. Which is not necessarily representative of the coarsening wet foam, but is sort of, and we also did it just taking an initial Voronoi tiling as the, using that to give directly the, so unweighted or anything like that, to give the bubble areas. And we find, we haven't necessarily compared absolutely every result, but in general, our impression is that the results are qualitatively the same. So we wouldn't expect this to be quantitative for every foam, but in terms of, so maybe as an example, with the growth rates, I mean, clearly, maybe it's trivial in this case because von Neumann's law should give the exact result, but in the Voronoi foam using just the areas given by the Voronoi tiling directly, you sort of just see a sort of compression of the same, as in the sort of, the distribution is the realized parts of the distribution of growth rates is narrowed in terms of radius, if that makes sense. So the middle portion of this plot is well covered by points, but you don't get many points over here and you don't get many points over here. And so that's one of the reasons that we like, I like this distribution, is that it is very polydispersed, probably too polydispersed for the scaling state, I think. But nevertheless, it fills out these areas that might not be well covered otherwise, I think.
Very nice.
You should not think that the scaling state is the most important one. If that was, you heard in my talk, I think on Earth the most important state is not the scaling state, but what you have on Earth, which is frames which are like these, which didn't have the time to get towards the scaling state. So far, theory has only been able to say something about the scaling state, as well as the present state of affairs in theory that focuses on scaling states, and everything before the scaling state is very relevant, I would say.
Great. Thank you very much, David.